is Isabel. I'm a PhD student at University of São Paulo in Brazil. And first I'd like to thank the organizers for just giving me the opportunity to be here and present a bit of my work. So today I'm going to talk about our study of the scaling relation between the X-ray luminosity and the mass using a unified weak lensing sample of galaxy clusters. So since we're all attending this meeting, I believe we're all very familiar with galaxy clusters, but just real briefly, we know these structures can be extremely massive. We know they have this intercluster medium, the ASIAA, which is this very hot, diffuse plasma. And the thing here is that this ASIAA is a very strong X-ray emitter. So I'm just showing an example in the optical of a cluster, and over here I'm just showing the same image, but now overlapped with an X-ray image by Chandra telescope, just to show this very strong X-ray emission. And we also know that it's very important to trying to estimate the mass of the clusters, especially for cosmological studies, since the number density of clusters as a function of their mass can be a good proxy for some cosmological parameters such as the matter density and sigma 8. So basically to do some plots like this that we've seen a lot in many presentations here. But actually to constrain those parameters we actually need to work with a very large sample of clusters. And in that case, methods that we consider more direct to measure the mass can be very challenging. And that's why we usually rely in scaling relations. That basically can tell us the mass of the cluster based on another cluster property that's easier to obtain, such as X-ray luminosity. So that's why we want to study this relation. And for that, we actually used the extended version of the Codex catalog. The Codex catalog is actually a reanalysis of the Rosat-All-Sky survey, which is a relatively old X-ray survey. But with Codex, we can actually extend the flux limits by also making a double identification on the optical using the legacy surveys. So in the end, this new Codex legacy catalog covers 14,000 square degrees, and in the clean catalog, we have over 4,000 sources. So I just want to note here that we just published those catalogs, so if you want more information about them, and if you want access to the entire catalog, please feel free to reach me. We'll be very happy to provide this information. So moving forward, this is where we get our X-ray informations. And as for the mass informations, we actually decided to go with weak lensing estimates, and that's because this method is sensible to the entire mass of the clusters, but not too sensible to the dynamical state of the cluster. And for this work, we actually used 3 previously published samples. We used one from Erbonnet et al. 2020, another from Oguri et al. 2021, and the third here that I'm calling main subsample is actually an extension of a previous work done by a member of our collaboration. So in the end, we are working with a sample of 100 Codex clusters that we have weak lensing mass estimates. And over here, I'm just showing the distribution in redshift that goes from 0.1 to 0.65. Which is a relatively wide range in redshift, and that's good actually because we don't only want to calibrate the scaling relation, we actually want to see if that relation can evolve with the redshift. So what is this relation, right? So we have this theoretical prediction from the self-similar model that basically tells us that the relation should follow a power law, which in log space is just a simple linear relation that we actually add a new term just to account for this possible redshift evolution. So in principle, we would expect the slope to be something similar to this exponent here, but for this work, we actually decided to compare with a more recent paper that actually accounted for effects of temperature and metallicity on the ICM. So we will be comparing our results with the self-similar prediction of 0.9 for the slope, and in principle, we wouldn't expect any evolution. So this gamma parameter here should be around 0. So we didn't want to make just a simple linear fit. This was done before. We actually wanted to create a Bayesian model that accounted for effects of biases and selection effects. So we've seen already many presentations that talked about this importance of those effects when dealing with cluster cosmology. But just to illustrate a little bit how these effects work, I'm showing here the log of luminosity, the log of mass, and let's just assume that the true scaling relation that we want to recover is this red line here. So we can already see that the data is scattered around that, but a more realistic representation would be something like this, because we have the halo mass function, meaning when we are looking to the universe, we see much more lower mass structures than high mass structures. And of course, whenever you're making observations, you have to deal with flux limits. So there's a threshold, and beyond that, your source is just too faint and you cannot observe, so we end up losing a lot of points. Of course, whenever you're constructing your catalog and your sample, you're gonna have to make some selection effects, some selections, and in the end, you also have measurement errors. So if you just make a simple linear fit without taking those things into considerations, you're gonna end up with a scaling relation that no longer represents that original cluster population. So that was the idea. I don't have much time to enter much in detail on those mathematical parts, but this is our likelihood function. So we model functions, So we model functions that accounted for intrinsic scatter and measurement errors for both the X-ray luminosity and the mass. We accounted for the halo mass function and the effective volume that we were working with. And perhaps the most important part of this work was the modeling of the selection effects. And basically we tried to model for pretty much every important selection we could think of. Just briefly here, we accounted for the effects of completeness in detecting clusters both in the X-ray and in the optical, because codecs we have this double identification. We also model a function that basically tells us how much representative our sample is of the entire cluster population. We also made another function that, based on simulation, it tells us the probability of a cluster being detected in the codex catalog. And last, but definitely not least, is the relation between cluster richness and mass. And that's because many of our selections here are based on the richness. And we know the richness correlates with the mass. So we had to take these things into consideration, and what we found was actually these terms to be very important when constraining our parameters. So we took that likelihood and we made an MCMC fitting, and basically those are our results. We have here the X-ray luminosity and the mass and our main fit. And basically what we found was a slope value smaller than what we would expect from self-similarity by 1.7 sigma. And as for the evolution parameter, it is consistent with 0 within 1.5 sigma, which basically tells us that we did not find any strong evidence for evolution. But because we found that small value for the slope, we actually wanted to investigate a little bit further. So we also use eROSITA data. And that's because eROSITA has a much better spatial resolution, so we can actually compute the X-ray luminosity excluding the core region of the cluster. We were able to do that for 42 clusters of that original 100 sample that we had. Over here I'm just showing the eROSITA luminosity versus the codex luminosity. So we can see they are in fairly good agreement, no systematic difference here. And we made the entire fit again. And what we found was actually a much better agreement with self-similarity. So the slope value actually agrees within 1 sigma, and the evolution parameter really couldn't be closer to 0. And what that tells us is that whenever you're calibrating this relation, there is indeed an effect of flux contamination in the core regions. And that's because on those regions, as we know, we have effects of cooling flow and AGN feedback. So if you have the spatial resolution for it, whenever you're making these estimations, perhaps it's better to use quark-excited X-ray luminosity. We also compare our results with the literature, and generally speaking, we found the slope parameters to be smaller than what was previously published. Here I'm comparing the slope. And we actually justify this by the fact that we are using very high mass clusters in our sample, and we would indeed expect a difference in behavior when we are dealing with high mass and low mass cluster samples. As for the evolution parameter, it is in agreement with previously published works, and basically tells us that we still don't find any strong evidence for evolution. And maybe what this physically means is that non-gravitational processes such as AGNs and such, their dependence on the redshift actually doesn't affect much our scalar relation. So that's it. I'm going to leave you with a few of my conclusions from this work, and just finish by saying that this work actually provided the practical means to make future cosmological studies, not only with certain perhaps older data from ROSA, but with more recent data with eROSITA. So, well, that's it. Thank you, and I'll be happy to answer any questions.
Okay, questions for Isabel?
So I have a question about the scatter in scaling relation. So you just assume the constant value for the scatter, or the scatter is a function of mass or redshift, or that dependence is somehow effectively included in selection functions, or self function seems to be, it depends on the like richness or something like that.
Okay, so the scatter of our relation, redshift, X-ray luminosity and mass relation is actually a parameter for us, but we accounted for, let me go back over here, just a line. Okay, right here I can use it. Over here on the simulations, we actually, the simulations actually account for the X-ray luminosity and mass relation. So it does depend on the intrinsic scatter, but what we actually did was interpolate the simulations within our MCMC fitting. And as for the scatter in the richness mass relation, we actually used a previously published work this year that used codex clusters as well for constraining the richness mass relation. So we used their value for the scatter.
Right. My question is going to be about the scatter too. So maybe So overall, the scatter in the LX simulation looked a little low, I guess, especially since it's core included, like within what I would have expected, if I'm interpreting your number correctly. So I'm just wondering, so I was going to ask a little bit related to the scatter, like, do you have any explanation for that, or could it be that, maybe if you overestimate the scatter in the lambda mass relation, would then that underestimate the scatter that you're getting from the LX-M relation?
Yeah, thank you for that question. Actually, the referee of the paper actually asked that. But we, because we found this relation to be very important for our results, we actually made we used this relation, and we scattered up and scattered down and made the entire fit again to see if it would change much our results, and it didn't. So it's not that much important in the end. I mean, accounting for the relation, yes, it's important, but small variations in scatter, it's not that much. And as for you said it was a small value for the slope for which relation?
No, a small value in the scatter.
The scatter,
Yeah, the quark size luminosity would have a smaller scatter with mass than, maybe even like the ROSA ERAS comparison showed any signs of what was explaining that.
Yeah, no, actually I don't know. You're saying, oh, I don't show in here the results for the scatter of the Rosita, right? But I do have them in here. Okay, that may scare a little bit. We made many fits, changing a lot of parameters just to see how much it affects everything. So Rosita is right here, and we do have a smaller scatter, a little bit higher actually. But it's an agreement actually. I don't think we can directly say it's bigger or smaller in that sense.
Why don't we thank Isabel one more time?